In this video, we're going to look at an introduction to calculus and focus on differentiation. Calculus is a branch of maths that studies change. When we're talking about differentiation or the derivative, we're looking at the rate of change of one variable with respect to another. If we see now the notation dy by dx, this looks at the rate of change of y with respect to x. You'll often see dy by dx as x and y are common variables. Let's go back now to the slope of a straight line. If we have a straight line, we can easily see the gradient of this line by picking 2 points. So for example, if I had 1, 2 and I had this point now 5, 10, we could say that the gradient now was the change in y over the change in x. So this would give me 10 minus 2 over 5 minus 1. If we look at that now, that's going to give me 8 over 4, and we can say that the gradient is a constant value of 2. This is not always going to be the case, especially when we have a curve. We can't just pick 2 points and say that we have this constant gradient. Dy by dx gives us what we call the gradient function, and that will give us now the gradient of a slope at any point. So let's look at a particular curve. So here it looks like we've got a cubic function. What we've got is the tangent to the curve, and that tangent touches at any given point. We can see that the gradient of this line is fairly steep. As the tangent moves around the curve, that is going to change in terms of how steep this line is. So if we just move it now slowly, what we can see is that now the gradient is 0, and if we move it slowly round, we've got now a negative gradient. If we move it round, we will see, and just moving it around slowly, it's getting steeper but still negative. Then it will come round to the top, and again it will become flat, so the gradient will be 0, and we call this a stationary point, and then the tangent will again have a positive gradient, but we can see now that the gradient of this line here at any particular point on the slope will be changing. We use dy by dx, if our variables are x and y, to find now the gradient of a curve at any given point. In this video, we're just going to look at basic differentiation of powers of x. So if we have now y is equal to a function of x, and we could have now, let's just write this as y is equal to now x to the power of n, we can say that dy by dx, the gradient function or the first derivative, is given now as n multiplied by x to the power of n minus 1. Essentially what we're saying here is that we multiply down by the power and drop the power by 1 if we simply have powers of x. In later topics or courses you will look at differentiating trig functions and exponential functions, but for now if we're just differentiating powers of x, then we have dy by dx is going to be n x to the n minus 1. So let's say we did have that cubic function, and let's say that cubic function was y is equal to x cubed plus 4x squared plus 2x plus 1. We might be asked to find the derivative, dy by dx, or the gradient function. If I did this, it would allow me to find now the initially the gradient and then the equation of the tangent to the curve at a given point. So we differentiate both sides of this equation with respect to x. The derivative of y with respect to x can be written as dy by dx. So I multiply down and I've got a little 1 here, so that's going to be 3 lots of 1, which is 3, and I drop the power by 1. I multiply down by the power, which becomes 8, and I write my x and drop the power by 1. Here what we've got is a little power of 1. I multiply down by the power and I drop the power now by 1. Here comes an interesting point. This here is going to be 1x to the 0. When we multiply down, we're going to end up with 0. When we differentiate a constant, so that's a term independent of x, we get 0. I'm just going to look at each of these in turn to give you a more intuitive understanding of why differentiating a constant 0, and we'll tidy this up a minute then look at that. So 3x squared plus 8x plus 2. This gives me now the gradient function. So for example, if I wanted to find now the gradient of the slope at a given point, i.e. the gradient of a tangent at that given point, let's say that at that point that was going to be x is equal to 1. We could say now at x is equal to 1, dy by dx is going to be equal to 3 lots of 1 squared, which is 3, plus 8 lots of 1, which is going to be 8, plus 2. And that's going to give me 13. So if we had this curve, and let's just go ahead, let's say it looks something like so. At the point now where x is going to be equal to 1, we would have now this gradient, and this would be 13. So that's what this is telling us. What I want to do though is just look at these two terms in particular to give you some idea of why the derivative, let's just write this, the derivative with respect to x of 2x is going to give us 2. Remember, this is the gradient function. If we go back to this line, what we can see is that we have the line y is equal to 2x. So if we wanted to find dy by dx, which is part of this polynomial in the cubic equation, then we can see that it's going to have a constant gradient of 2. So if we think about this now as a standalone function, y is equal to 2x, quite clearly we're going to have a constant gradient of 2. If I had now this term here, y is equal to 3x, differentiating it would give us 3, and it would be constant. If we look at this constant value, let's go ahead and draw this, and I'll just put some axes here. So what we'll have now, let's go ahead and put this on. If I had the line now, and this would be the line y is equal to 1. If we look at the gradient here, so let's go ahead and do that. So y is equal to 1. The gradient of this line, m, is going to be equal to 0, and that will be constant. So when we've got the derivative with respect to x of a constant, let's say in this case, let's go for 5, this is going to be 0, because the gradient of the line y is equal to 5 is 0. If you wanted an alternative, more mechanical, so less intuitive way of looking at that, if we've got y is equal to 5, we can write this as 5x to the 0. Remember, x to the 0 is 1. So dy by dx, if we multiply down by the power, 0 times by 5 is going to be equal to 0. So as soon as we multiply down by this power, differentiating a constant will give us 0. So that's a more mechanical, less intuitive way, but if you wanted to take these bits apart, you could see now that of why differentiating a term in x gives us a constant value, and differentiating a constant gives us 0. And these are the things students often, they're perfectly fine with the higher order powers. So for example now, if we said if y is equal to 4x to the power 5, most students would just simply write that dy by dx is going to be equal to 20x to the 4th. They've multiplied down by the power, which is perfectly fine. The derivative now of a quintic function will be a quartic function. If a student had y is equal to 10x cubed, then they would write down that the derivative dy by dx is going to be 30x squared. The issues come when they have something along the lines of y is equal to 4x, and they just don't seem to write down what the derivative is for some reason. And another one, y is equal to 5. This again is a constant. Differentiating this would give us 0. Differentiating this will give us 4. It's a constant gradient. So that's why I spent a little more time on that. So that's the take-home message. dy by dx considers the rate of change of y with respect to x. It's the gradient function, and if we find the gradient function of a function, we can go ahead and find the slope gradient at any given point by simply substituting in the x coordinate. So we could clearly see now with this one, if I took the x coordinate just here and substituted it in, we would have a different gradient to the one we've just looked at. If I chose it here, quite clearly a different one. And that is why it's important that we can use this derivative, as we can't simply use a straight line. A straight line would prove to be a secant, and that wouldn't give us now the instantaneous rate of change of the function. So let's just go ahead and practice these. So let's just write now, if y, so let's write this here, if y is equal to x to the power of n, then dy dx, let's just write this here, dy by dx, the gradient function, or the first derivative, is going to be nx to the n minus 1. I said the first derivative, we can keep going with this. We can have the second derivative, d2y by dx squared. We will look at that in later videos. This is the rate of change of the rate of change, or how is that tangent line changing. But let's just focus on this. This is the first derivative. So that's what we've got. So let's look at the first one. Y is equal to 2x. So this again is 2x to the 1. So dy by dx, the gradient function, or the first derivative, is simply going to be 2. We multiply down by the power and drop the power by 1. If you're in your infancy and you want to show your teacher you know what you're doing, you could write now that this is going to be 2x to the 0, which is simply going to be 2. We know that the gradient of a line, 2x, is going to have now the gradient 2. That's nice and straightforward. The next one, y is equal to 3x squared. So this is a parabola, it's a quadratic function, and if we just sketch that up, what we would see is that we do have a change in value of the gradient at given points. To the left of the y-axis, we will have a negative gradient for the tangent, and then to the right, we're going to have a positive one. So if I just drew some tangent lines on here, we might have this one just here. We'll have one at 0, which will be flat. It will be parallel to the x-axis. The gradient will be 0. And that's what we call a stationary point. And again, we'll look at that in later videos. We can see we've got a positive gradient. We can see that we got a steeper negative gradient. We can see that we got a steeper positive gradient. So what we're going to find with this particular function, when we take dy by dx, the gradient function, so differentiating both sides of the equation with respect to x, this will give me 6x, or 6x to the power of 1. So if I substituted in, let's pick this point just here. Let's say that at this point, x was equal to 1. The tangent here, the gradient therefore, is going to be equal to 6 times by 1, which is 6. Yet if I chose this point right here, and this point was x is equal to 2, then what we're going to have is that the gradient is going to be 6 times by 2, so we can say m is equal to 12. If we picked a point just here, let's say that this is going to be negative 3, so x will be equal to negative 3, then m, the gradient, is going to be 6 lots of negative 3, so that's negative 18. So that's a very negative steep line. And of course, as the curve goes up, we're going to get steeper and steeper, more negative. If we chose this point right here and we said x was equal to negative 1/2, then dy by dx when x is negative half would give us negative 3. So a less steep line, and we could say that the gradient of that point on the curve is going to be negative 3. Okay, if y is equal to 4, so y is equal to 4 dy by dx, so dy by dx is going to be equal to 0. Differentiating a constant gives us 0. The last one here, we've got now a quadratic function, so another parabola, or if you like, we can say that this is a polynomial. So y is equal to 5x squared minus 3x plus 1. dy by dx, differentiating both sides of this equation with respect to x, we'll have now 10x to the power of 1. Remember, that's a little 1, so we'll have minus 3x to the power of 0. Differentiating a constant gives us 0. Tidying this up, I would simply write this now as 10x minus 3. So if we wanted to find now the gradient at any point on this curve, we would simply substitute the x coordinate in here. So for example, if I wanted the gradient when x was equal to 1, we could see that m would be equal to 10 times by 1 minus 3, the gradient would be 7. If we wanted it when x was going to be equal to 10, we would have now the gradient is 10 times 10 minus 3, which is going to give me now 97. So that's what we would have. Before we move on, I'm just going to look now at using function notation. If we have a function of x, f of x is equal to, and let's just write a function. So let's have 4x to the fifth minus 3x squared plus 2x. We would say the first derivative is f dashed of x. So what we've got is the function, its gradient function is f dashed. When we looked at d2y by dx squared, the second derivative, let's just go back. Let's go ahead and look at that. When we looked at the second derivative, did we write it down, or was that in a previous? Okay, well, we'll just now write first derivative. We'll come back to second derivative. If we have the first derivative, there's the second derivative, d2y by dx squared. I knew I'd written it somewhere. We would say that that would be f double dashed of x. So that would be the second derivative. And again, that would be the rate of change of the rate of change. And we can do successive derivatives on here. Ultimately, we'll get naught with this particular function. But here, what we'd have now, the first derivative, f dashed of x, multiplying down, that's going to give me 20, drop the power by 1, 4. Multiplied down by the power, that's going to give me now on here, that's going to give me 6x to the power of 1, or just 6x, and then we're going to have plus 2. So if I differentiate it again, what would we have? 80x cubed minus 6, and then plus 0. So that's the second derivative. So I'm just taking successive derivatives. And of course, we could keep going down. As this is an integer power, positive integer power of x, we would simply get down to x to the 0. But yeah, this is just alternative notation. If y is equal to a function of x, dy by dx is nx to the n minus 1. This is exactly the same. We're just using function notation. This is a function, and this here is the derivative. Generally speaking, we use y and x, but that won't always be the case. So in here, question 2, we're asked to find ds dt. S is generally displacement and t is time. So exactly the same. We would differentiate both sides of this equation with respect to t. So we would have ds dt on the left. So how is s changing as t does? Multiply down by the power, drop the power by 1. The further you go into your work with differentiation, the less you have to show full workings, as it were. So I'm just going to simply write down that this is going to be 12t squared. So that is an expression in terms of t for ds dt. This is the first derivative of a gradient function. The next one, let's go ahead, differentiate both sides with respect to t, ds dt. So we're going to have 10, that's going to give me now 10t to the fourth. And then we're going to have minus 3. And then, of course, if you want to show you know what you're doing, you can add 0. But if you were asked for it in its simplest form and there were no specific marks for working, this would be perfectly fine. Here, we need to expand the brackets. So if we just go ahead and do that, let's just expand the brackets. So we're going to have, we'll have t squared, then we're going to have plus 1t, and then we're going to have minus 2. In later topics, you'll see something called the product rule, when we have a multiple of two functions. I'm not going to use it for this. Quite clearly, we can just expand this out. But for techniques later on, when we have more complicated functions, then you'd use the product rule, where you have two functions of t multiplied by one another. Okay, ds dt is going to be equal to 2t plus 1. So nice and straightforward. So this gives us a gradient function now of this quadratic, and we of course have a linear function. When we're differentiating, we can see that if we have a quadratic, we would have a linear gradient function. If we had a cubic, then we'd have a quadratic gradient function. If we had a quartic, we'd have a cubic, and so on. So essentially the derivative in terms of these polynomials, when we've got positive integer powers, is just going to be 1 less. So they are the basic techniques to differentiate powers of x. We've looked at powers of t, but again, what we're not differentiating, for example, is y is equal to e to the power of 2x. We're not differentiating y is equal to sine of 3x. We're not differentiating y is equal to the natural log of 4x. These are simply now powers of x. In the next video, we will look at some more challenging examples where we might have to simplify and we have fractional or negative powers. So hopefully that's been a good intro to calculus and differentiation in particular, and then we'll move on from here.